All right, so we're looking at projectiles at an angle. That's the topic for today. These can be a little bit tricky. There's kind of a lot involved, so we'll kind of go through each step, talk some math, talk some conceptual stuff, and hopefully make our way through it. Here, just to refresh, I put our horizontal equation and vertical equations on here. Now, we already talked about these previously when we talked about horizontally launched projectiles, so those should be pretty familiar. They should be pretty familiar from chapter 2 anyway. But those are going to be used again. We're going to see a couple new additions to that, just some specialty equations. But overall, most of the solving that you'll do for these problems comes from these equations, okay? One big difference now is that these things are going to get launched at some kind of an angle. So I'm going to draw a representation of that. So let's say we're launching or kicking a ball, all right? I'm going to draw you a nice picture. All right, there's the ball. We're launching this thing through the air. Let's just assign it some kind of a velocity or a speed, let's say 10 meters per second. So there it is. If you notice, because it's at an angle, just like we've been harping the entire chapter, if something's at an angle, then it has both an X and a Y component. And we've solved these out. You've probably done 100 of them by now. And that's going to be really important to realize with these problems as well. So something that's launched at this angle, it has an X component and it has a Y component, just like everything else in this chapter has. Those are going to be very important. So this a lot of times will get called the launch velocity. Sometimes it'll get called the initial velocity, like the VI or launch speed or launch velocity. And then these guys will be like the VX, velocity in the X direction. So we can call this VX. And then this can be called the VY. So I'm just going to scribble these out now that we don't need those anymore. So you can see the two components. There's the horizontal component of the velocity, and then there's the vertical component of the velocity. These are going to be important because these can be used with these equations over here. This launch velocity, this initial velocity, the way we have it labeled, this can't be plugged into any of these equations because these equations call for either horizontal velocities or vertical velocities. This has both. And so that can't be plugged into any of the equations. So it's useful only up to a certain point. Really, like this number is going to be useful so that we can get Vx and Vy. So just running cosine and sine to solve those. Once we get those two components, this becomes kind of obsolete almost and won't be something that you need after that point. So that's probably the most important thing to realize. And where I see a lot of people struggle is they don't understand the two parts to these projectiles at an angle, the X and the Y. So as long as you can do the little triangle thing here, then you get these velocities and it's kind of back to chapter 2 stuff. Use your equations and solve out whatever you need. So keep that in mind. That's a big part. All right, what else do we have here? Let's draw out flight path here. We're still talking flight path of a parabola, which we already discussed when we talked about projectiles launched horizontally. So something that looks like this, now that we're looking at things launched at an angle. So over here basically is what we drew up here with this triangle. All right. Some similarities what we saw when we launched things horizontally. Those similarities being, if you remember, we talked about this Vx being constant throughout the problem. So we said that we can draw this little triangle in down here if we want to, just so it kind of mirrors what we have up here. This V and then Vx here, Vy here. This Vx stays constant throughout the problem. That didn't change since we talked about horizontal projectiles. So if Vx, if we assign this a value of, let's just say like 5 meters per second, then if you put a dot here, the Vx is going to be 5 meters per second. You put a dot over here, the Vx is going to be 5 meters per second. And you get the idea. No matter where we would put a dot, Vx will be 5 meters per second. Vy is going to be different. So you're going to have a velocity here in the y direction to start with, just like we would solve up here with this triangle. And as this thing goes up, as it flies and approaches its highest point, the Vy is going to decrease because gravity is going to be accelerating it downwards, and you're going to see Vy go down. And then once it gets on the other side and starts to come back down, just like an object in free fall, that velocity or that speed is going to get faster and faster and faster until it smacks into the ground over here. So Vy is going to be constantly changing as it follows this parabola. Vx is not. Vx is going to be constant because that's the way we defined it. Neglecting air resistance, that value won't change. Okay, so hopefully that's kind of a good review of us talking about Vx not changing in these problems once you figure it out, which would be done just with a little bit of triangle work, a little bit of cosine down here. Other important things to note, really, really important, is if we draw just an arrow to point out this highest point, like the apex of this projectile, the highest point that it achieves, just like an object that's in free fall, like we throw something straight up, once it gets to its highest point, we would say that its final velocity at that highest point is 0 before it starts to come back down. This is going to be no different. And so here we have to define this because we're talking about the Vy now, but up here at the highest point, so the very top, Vy right there is going to be 0 before it starts to come back down. So you're going to have a situation where Vy decreases, 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 reaches 0, and then increases, increases, increases until it smacks into the ground. So a lot of times, like when we're solving stuff, being able to plug in that 0 into these equations, remember this is a vertical component, so it'd have to be these vertical equations, but being able to know that 0 a lot of times allows us to put numbers in where it doesn't seem like we have enough information. So like right here with Vf, right here with Vf. So keep that in mind, especially if you're solving like the height that the projectile reaches, how high above the ground it is. A lot of times being able to plug that in will really help. All right, another thing we could do here is I can draw kind of a dashed line just to separate this out. You can kind of tell it, I think, by looking at it, but when we're looking at time, the amount of time that it takes to get to its highest point versus coming back down to the same height, as long as these 2 points are equal heights, the time that it takes to go up equals, try to fill that in, the amount of time that it takes to come back down. So a lot of times there might be a situation where we want to know how long this thing's in the air, and we might have enough information to figure out how long it takes to get to its highest point. Well, if we just double that, then we would have the amount of time that it would take to come all the way back down. So the time up equals the time down. Now the acceleration in the y direction is going to be gravity. So throughout this whole problem, so no matter where you're at, start to finish, the acceleration is always going to be 9.8 meters per second squared. And remember, we put a negative sign on that just to signify that that's going to be in the downward direction. Acceleration in the x direction, there is none because we've defined Vx as constant. So it's not changing speed, not changing velocity. So the Vx, no acceleration. The acceleration in the y direction is just going to be gravity, 9.8 meters per second squared. Okay, so hopefully that makes some sense and helps you get those things set up. We can look at some of these launch angles in determining like what angle will give us the maximum height something could go, what launch angle would give us the maximum distance, what angle will keep something in the air for the longest. So we have just kind of a list of things to kind of discuss. Put these down here maybe at the bottom. So let's look at some launch angles. Launch angles. All right, let's do maximum distance first. Max distance. So think about this, and this parabola is kind of cool to look at when you're thinking about all of these. What launch angle, so if I put theta in here, what launch angle will make this projectile go the farthest? So if we want something to land as far away as possible, this dx component as we've called it, what angle will allow it to go the farthest? Well, to kind of think about this, we need a couple things. We've got velocity in the x direction, we've got velocity in the y direction. And we need some kind of a happy medium in between the two because we need this thing to be going horizontally, but then we also need it to stay in the air. And so the magic number for maximum distance is going to be 45 degrees. That makes it go the farthest. If you increase that a little bit, so in other words, if this is our 45-degree angle, if we launch at a greater height, it's going to stay in the air longer, which is nice, but as we do this, the Vx decreases. So we're not going to have as much Vx, which means less dx overall. Ultimately here, what we're looking at is this equation, right? And if we're going for maximum distance, which is our dx, we're doing Vx times t. And so we want a big Vx and a big t if we want a large dx. And so that's kind of the middle ground here, because once we get past 45 degrees, our Vx decreases and it turns more into Vy. And then likewise, if we go below that 45 degree, what decreases? Well, the time decreases because it's not going to go as high. And so 45, the reason that it is 45 is it maintains as much Vx as possible and keeps the thing in the air for kind of a happy medium amount of time as well, so that it can cover some distance. So 45 degree max distance angle. All right, let's see, what else could we do? We could do maximum height. So if you have this projectile, say like a Nerf gun or something like that, and you want it to go the highest it can possibly go, what's the maximum launch angle? Well, think about it, it would be 90 degrees, so it would be straight up, because then all of the velocity is going towards carrying that up instead of left and right in the x direction. So max height, you're going to fire the thing straight up. Could do something called like hang time. In other words, if you wanted the projectile to stay in the air the longest, what angle would you launch it at? Well, time for these is directly related to height. And so the one that gets it to go the highest will keep it in the air the longest. So again, you would fire this thing straight up if you wanted to get it to stay in the air the longest. And then the last one, which is kind of interesting, is launch angles that would make the projectile go the same distance. So there are certain angles that if you launch them at either angle, it will make it go an equal distance dx. Turns out these just have to be the same distance away from 45 degrees. So I'll just kind of write same distance from 45 degrees, and then I'll explain what that means. If you, let's just say, let's deviate this and launch something at a 46 degree angle and launch something at a 44 degree angle. If you noticed, each of these is only 1 degree away from 45. That means that these will go the exact same distance. And so this will work with any combination as long as it's an equal distance from 45 degrees. So you could go something like 20 degree difference. So we could go up to 65 degrees and then go down to 25 degrees. These will land in the exact same spot. Now their flight paths will be a lot different. Like if you think about launching something at a 65 degree angle, which is kind of steep, it's gonna look something like that. 25 is kind of a shallow launch angle. It's gonna look something like this. But if you notice, this dx here is the same. They meet up at the same point, even though their flight paths look different. So, like I said, you can make any combination that you want there as long as they are an equal distance from 45. All right, awesome. So that's kind of the run through. I know that's not much of a run through. There's a lot of detail there. That gets you thinking about the right things. The last couple things to look at are some specialty equations. These would never be needed on the AP test. I like to include them just because they can kind of solve out some things relatively quickly. So from here on that top one, that one's set up to solve for VI. That is the launch velocity. And really, if you look at it, you don't need to know a whole lot to figure out the launch speed. You need to know how far the thing would go. There's dx. G, of course, we know as long as we're talking about the Earth. And then the only other thing is the angle. So if you know the angle that it's launched and how far it goes, you can figure out the launch speed, which is VI. So you'll need to have that one memorized. And then the other one, this one will help you solve for launch angles. So if you need to figure out like at what angle something was launched and you know the dx, how far it goes, and how fast it was launched, VI. Notice these are actually VIs. These are launch speeds. None of the other equations are, allow you to enter these numbers. So these are definitely specialty equations. But if you know how far it goes and its launch speed, you can plug in here. Right there's your angle, so you have to solve for theta. And the way to do this equation is to plug in numbers, solve, get a number, take inverse sine, divide by 2. You got to do it in that order for it to work out. So get a number, inverse sine to get rid of sine, and then divide by 2, and that'll help you solve out your angle. So those are the only specialty equations that you'll need. Lastly, I thought we'd run through a quick example. So let me put a problem up here, and then let's actually solve out some of these things. just to give you a little bit of practice. So this one, we've got an archer firing an arrow at a 43-degree angle. I would always sketch these out. I think that's just a good move. To give you a little bit of a visual, I'll do it down here. We've got room 43 degrees. Here's triangle. It wants us to solve launch velocity, so we're solving VI. This is what part A wants, and to solve that we have the specialty equation that I just showed you in the previous screen. So this guy, write that all out. Takes a little getting used to, kind of a weird equation, and then actually plug some values in, which I'll do down here. We're going to enter G as a positive, so we don't end up with a negative underneath this radical. We got dx. This thing goes 215 meters. Then we got sine of our angle, which is 43, and cosine of our angle, 43. So a lot of calculator entry on this thing. I'm going to go ahead and run that through. I like to separate mine out. I'm always paranoid about calculator mistakes. Okay. So I'm getting a VI, assuming we go back to 2 sigs, we're going to get a launch velocity here of 46 meters per second. So if everything went right, you entered that into your calculator right, going back to 2 sigs based on that angle, launch velocity of 46 meters per second. So that's part A. Just using that specialty equation, we now know that this is, I'll go ahead and write it on, 46 meters per second. Next up, time in the air. Now I know basically if the problem asks for anything except this launch velocity, I can't use any other equation, which I'm going to have to do here to solve some stuff. I can't use any of the other equations without knowing Vx and Vy. And so I'm just going to solve these out. We've done a lot of these triangles, so I won't put too much into the explanation other than saying I'm going to use cosine to solve Vx, and I'm going to use sine to solve Vy. And I think that's probably enough for you guys to work your way through it. So Vx comes out to be, if we just stick with 2 sigs on everything, let's call it 34 meters per second. And Vy over here, using sine, I'm getting 31 meters per second there as well, which makes sense that those are pretty similar with a 43-degree angle. All right, so now we hop down here to part B. So these weren't really asked for. Nowhere in the problem did it say solve out the Vy and Vx, but I know if I'm doing more calculations, I'm going to need them. So that's why I did that. Time in the air. All right, so you've got some options here. You kind of picture this flying through the air. All we need is an equation that solves for t. And so probably the easiest thing would be looking at this equation, because we know Vx and we know dx, because I just solved Vx and dx is actually in the problem. So I could just rearrange this into, well, if I rearrange it the right way, dx over Vx. So we got dx here of 215, and our Vx that we solved for was 34. So we can just run that through. All right, I got a flight time here of 6.3 seconds. So that's probably the most straightforward way to do it. You also could have used vertical equations. I think you've got enough here. Probably what I would do is chop this in half and remember that Vy equals 0 on that. And then just solve how long it takes to get to the top and double it, since it'll take twice as long to get there. I can kind of show you that work as well if you want. So I'll put a line here. You wouldn't have to solve both of these, but that equation would look like this. Well, I take that back. We don't know the distance yet. Okay. So that one wouldn't work. I guess we'd have to use this guy. All right, that'll work. There's t. And then you would plug in 0 here. Initial velocity, you got to be careful. This will be Vy. So this guy right here. And then your 9.8 and solve out for time. So we can work that out if you'd like. 0 minus 31 over negative 9.8 equals, all right, we got 3.2 seconds. And remember that this is just on the way up. So we'll multiply this by 2, and we're going to come out with 6.4 seconds, which is basically identical to what we got over here on this side. So remember that last digit's always a guess digit anyway, so there's no difference between these two. So two different ways to approach that same problem. Like I said, this was probably the easier way, but this is a pretty good skill to have as well, to realize that you can solve the time on the way up and then just multiply by 2 to get total flight time. For part C says, what if this thing was not launched at an angle? What if this thing were just fired straight up? And so, in other words, kind of turns this back into a chapter 2 problem, which makes it easier because we're just going to fire this thing straight up. And we know that Vy up here at the top is 0. So we're going to use that to help out. We know the launch velocity down here is whatever we got up here, this 46, because this is now directed straight up. So now we know Vi, we know Vf, we know acceleration due to gravity. And this one wants maximum height, so here's where we're going to want to choose an equation that has, I guess I should put Vf squared instead of Vy squared. One that has d in it, that's what we want to solve for, and then we know everything else here. So I'm going to go Vf squared minus Vi squared over 2a equals d. And then we can plug in values. Final velocity, that thing's going to come to a stop all the way at the top. The initial velocity here, since we're actually firing this or launching this straight up, is the actual VI. So it's going to be 46 meters per second. We're going to divide that by 2, negative 9.8. And we're going to get our number. So that's a little bit tricky, like conceptually, to think this through, but you wouldn't use a Vy or a Vx here because there's no Vx and Vy component. It's all just one speed because it's launched straight up. So I'm going to reason that through. Let's see what we get here. Gosh, I think it goes pretty high. Calculator answer is this, and looks like we're going to stick with 2 sig, so this is going to round up to 110 meters if we fire that thing straight up into the air. All right, that's the run through. Hopefully that helps. I know it's a lot. You can tell just from that one problem how much I have written out there. But if you take it step by step, hopefully it's not too bad.